This next video is going to be showing you how to turn a standard form quadratic equation into vertex form, okay? And that's through a process that we like to call completing the square. All right. So once again, here's a reminder of what the three forms of a quadratic equation are. They are factored form, standard form, and vertex form. To get from factored to standard, you would have to expand or FOIL. To get, so FOIL, FOIL. To get from standard to factor, you'd have to factor. If you want to get from standard form to vertex form, you complete the square. That's a strategy that I'm going to show you in this video. And then if you want to get from vertex form back to standard form, you would expand again. Okay, so just as a quick minds on, what I'd like you to do, if you can, is pause the video and then do each of these questions where in the first three you're expanding and then in the second three you're factoring. I'll do them together for you, but like I say, it'd be good if you could pause or mute and then work on your own. Okay, so x plus 3 squared can also be written as x plus 3 times x plus 3. So then if you want to expand, you would have to multiply the first terms, the outside terms, the inside terms, and then the last terms. That's what FOIL stands for. So when you do that, you get x squared, that's x times x, and then x times 3 is 3x, and then 3 times x is 3x again, and then 3 times 3 is 9. Now you can collect like terms, and you'll get x squared plus 6x, the 3x and 3x together, plus 9. Okay, next one, similar. X minus 5 squared can also be written as x minus 5 times x minus 5. Now we'll do FOIL. X times x is x squared, x times negative 5 is negative 5x, negative 5 times x is negative 5x, negative 5 times negative 5 is positive 25. Okay, so those are all of our terms. Oops, plus 25, oops. Okay, now you collect like terms in the middle, the 5x and the 5x that are both negative together, and you'll get x squared minus 10x plus 25. Okay, one more like that that's a bit more general. X plus a times x plus a is the same thing as x plus a squared. X times x is x squared, x times a is ax, a times x again is ax, and a times a is a squared. When you collect like terms, that gives you x squared, and then we have ax and ax, which makes two ax's, plus a squared. Okay, what I want you to notice at this point is that there are some interesting things about all the numbers that we just did. So notice that this 3 was in that first expression. And then when we FOILed it out, we got a 6 in the middle and a 9 on the end. In the next one, we had a negative 5 in the middle. And then when we FOILed it out, we got a negative 10 in the middle and then a 25 in the end. In the last example, we had an A to start with. We ended up with a 2A. Oh, sorry, I didn't want that whole thing. I just wanted the 2A. In the middle, we have 2a, and on the end, we get a squared. So hopefully you can see the connection that I'm trying to draw, which is from this number that we started with to the middle number, you have to multiply by 2. Always true. This number times 2 is that middle number. This number times 2 is this middle number. Cool. And then if you notice the other pattern is that this number, when you square it, you get this number, okay? And this number, when you square it, you get this number. Same thing, okay? So whatever number you start with, if you multiply by 2, gives you the middle term of the standard form. And if you multiply it by itself, it gives you the last term of the standard form. Okay, so now let's go the other way. So we're starting with standard form this time and then working our way over to factored form. So we know when we factor, we're looking for 2 empty brackets. X and x would have to go at the start to give us x squared. And then there are possible numbers that could go here and here. It could be 6 and 6. It could be 12 and 3. But I'm going to go with 6 and 6. and then I'm going to check if that works. So x times x is x squared. X times 6 is 6x. 6 times x is 6x again. And 6 times 6 is 36. And when you collect like terms, that gives you x squared plus 12x plus 36, which means that we factored that correctly, okay? Because this one is equal to this one. So we did that right. So I'm going to erase my check. Okay, so that's our factored form, but since these two brackets are exactly the same, I could rewrite that as x plus 6 all squared, okay? Instead of saying x plus 6 times x plus 6, I could just say x plus 6 squared, meaning there's two of them being multiplied. Okay, in the next one, again, I'm factoring, so I'll put my two empty brackets. I know x and x have to go at the beginning to give us x squared. I'm looking for numbers that will multiply to give me 4 and also add up to give me negative 4. So it's probably going to be 2 and 2. But to give me that negative in the middle, I'm going to need them to be negative. So I could do my mental check. X times x is x squared. X times negative 2 is negative 2x. Here's another negative 2x together that gives me negative 4 in the middle. And then, of course, we get the positive 4 on the end. Okay, so once again, x minus 2, those are the same. So we can write it like this, x minus 2 squared. Okay, and then the last one, hopefully you're seeing the pattern here. X and x, two numbers that multiply to give you 121. I can think right off the top of my head, 11 times 11. 11 and 11 also add up to give me 22x. So that would be it. So I can rewrite those identical brackets being multiplied as x plus 11 all squared. Okay, so once again, I hope you can see some of the same patterns because they are still there. That if we look at this 6 that ends up in our final factored form, it is half of this one. So if you took this 6 multiplied by 2, you get that. Over here, if you took negative 2 multiplied by 2, you get this. And over here, if you took 11 and multiplied it by 2, you get 22. Okay? And same thing as before, where if you take that same number, that's 6, and you multiplied it by itself, you get 36. Same thing here. If you took this number, negative 2, multiplied by itself, you get 4. Over here, if you took that 11 multiplied by itself, you get 121. So the same pattern is still there. You multiply to get to the middle one, and multiply by 2 to get to the middle one, and then square to get to the second one. So all of these are called perfect squares. Okay, this is the name of all of these things, perfect squares. Okay, so what we're trying to do when we complete the square is we're trying to create this looking thing, okay? And the reason we're trying to do that is because if you know your vertex form looks like this. And as you can see, it contains a perfect square. Okay, it contains that bracketed section with two terms and a square, okay? So because we know that vertex form looks like that, we're going to try to force this kind of relationship to happen with the numbers that are in the equations that we're given, because we wanted to spit this nice thing at the end back at us, which will help us construct our vertex form. Okay, that's the kind of motivation behind it. So here are a bunch of examples. Okay, so if this one was a perfect square, then this last number right here would be half of this number squared. Because remember how that little bracket, it would have x and then some number. And that number in here is always half of the middle number. Okay, so that number, of course, would be negative 2 because that's half of negative 4. And then this number on the end would be what this number is multiplied by itself. Okay, which so would be negative 2 times negative 2, which is positive 4. So if this was a perfect square, then this number wouldn't be 7, it would be 4, but it's not. It's 7. But that's okay. What we can do is we can take what we have, y equals x squared minus 4x, and then, of course, there's this plus 7 that's already here. But we don't want the plus 7 to be there. We want 4 to be there. So we're just going to add 4. And the only way that we can do that without changing the whole equation is if we also subtract 4, so that it's kind of like we were never there. We add 4 because we want to create the perfect square, but we have to subtract 4 because we can't just change our equation. Okay, so now these first three terms are going to give us that perfect square because they have that relationship where there's a number that is half of this number and the square root of that number at the same time. And we know that that number is 2. So we can go ahead and put this perfect squared version of this bracketed section. So basically what we're doing is we're factoring. Okay, this step right here, we're factoring. You could go and do the long way to factor that, just so that you can convince yourself that that's what that really is. And now with the rest of the stuff, we just continue. We have now a -4 and a 7 on the outside of the brackets. That will simplify to 3. And there you go, we're done. That's a vertex form. I'll write it really nicely in one color so it doesn't look confusing. X minus 2 squared plus 3. Hopefully you recognize that as vertex form, because vertex form is y equals a x minus h squared plus k. It looks just like it, where the k is 3, the h is 2, and the a is 1. Okay, next example. Okay, so here we have y equals 2x squared minus 4x plus 7. Now, this one looks a little different than example 1 because it has this 2 at the front. And if you look back to that previous slide, none of those perfect squares had any coefficients on the x term. Okay, so they were all just regular x plus a number or x minus a number. So we need ours to be the same way for purposes in this course. So we don't want that 2 to be there. So since we don't want it to be there, we'll just get rid of it for a period of time. So I can get rid of it without actually removing it from my equation by factoring it out. Okay, so when I factor a 2 out of 2x squared, that leaves me with x squared, and that's nice and friendly because it's familiar to what we've been doing in the last examples that we just did. Okay, and when I factor 2 out of a -4x, that leaves me with -2x. Now, I know what you're thinking, I forgot about the 7, but I don't, if you know, like 2 doesn't go into 7, so it's going to give me a decimal or a fraction. And you know what? 7 is not going to be part of my perfect square anyway. If it was, I wouldn't have to complete the square would already be completed, or it would be very apparent. So I'm just going to leave the 7. He's not invited into my little bracket. Okay, I don't have to factor out the 2 because I don't really need him anyway. Okay, so I'm going to write this one more time, just so I give myself a little room in the places where I need it. Okay, so that's the same equation. I just spaced it out a little bit. So now is where I'm going to be creating the perfect square, and I'm kind of like ignoring all the stuff on the outside. I'm really just concerned about this bracket in the middle, because that bracket in the middle is where my perfect square is going to be living. So if this was a perfect square, I would find this third number by taking the middle number, which is -2, dividing it by 2, and then squaring the result. -2 divided by 2 is -1, and -1 squared is +1. So the number that I need right here is +1. However, I can't just add 1 to my whole equation without changing its value, so I have to also subtract 1 so that everybody's still happy. Okay? All right, so now the issue is that this part from here to here is the perfect square that I want, and now I have this little extra -1 that I don't really want to be there, but I had to put it there in order to make my equation equivalent to what it was before. So I'm going to remove it from that bracket. I don't want it to be there. However, because that bracket has a 2 in front of it, that means that the 2 is being multiplied by everything inside the bracket. So in order to release it from the grasp of that 2, I need to multiply it by 2. The 2 still has to have its sort of role on that number. So we're left with y equals 2 x squared minus 2x plus 1, which is nice because those are the only parts that I need. And then the -1 that we had, we moved outside of the brackets, but when we did that, we have to multiply it by 2. So now it becomes -2. We multiplied it by 2 because it had a coefficient of 2 on the front of the bracket. And then we have to add 7, which is still kicking around. The 7 has been here the whole time, and it's not really helpful to us at this point, but it has to stay there so that our equation is still true. Okay, and now finally, what we're going to do is we are going to factor that perfect square. And it's always going to look like that. It's always going to factor down to 2 brackets, to 1 bracket squared, or 2 identical brackets. And then that number that goes here is always going to be half of this middle number. Whatever your last line was, half of that number. So half of -2 is -1. And the 2 is still out front. Oh, sorry, I want that to be in black. So we still have the 2 out front, and now we're going to simplify the -2 plus 7, which gives us +5. And again, that is our final factored form. Nice. This time, the only difference, if you notice, if you look in our first example, we didn't have a number in the space, and this time we do. And that will happen anytime that from the start you have to factor something out. So anytime you have an a value, that same a value is going to spit back out at the end of your completing square process. Okay, another example. So this time, again, we have a coefficient out front, this -3, so we have to factor it out. So we have y equals, factor out the -3, and I'm only going to factor out the -3 from the first two terms because that -7 isn't going to be that helpful anyway, so and it's not divisible by 3, so I'll just leave it out there so it doesn't confuse things further. So 3 times x squared would give us 3x squared, and -3 times positive 6 x would give us negative 18x. Okay, so now I factored it 3. That's great. I'm going to write it again, but just space things out a little bit with a -3 at front. X squared plus 6x, and then the -7 on the end. And now I'm looking for that special number again that I have to add and subtract. I usually call it the special number, okay? So I'm looking for this middle one. So I'm going to take that middle one, the plus 6, I'm going to divide it by 2, and then I'm going to square it. So 6 divided by 2 is 3, and 3 squared is 9. So I add 9 because I want to, and then I subtract 9 because I have to, so that I don't actually change my equation's value. All right, so that leaves us with y equals -3 x squared plus 6x plus 9, and I want to end the bracket there, but there's this -9 again that's in my way. It's not part of my perfect square, so I don't want it to be there. So I want to remove it from the brackets, but before I do, it has to be multiplied by the coefficient on the bracket, which is -3. So I multiply by -3. So -9 times -3 is positive, 27. I'll put that in black so you can see it better. So positive 27. And then, of course, there is the -7 from before. Sorry that it's not on the same line. Okay, so that leaves us with y equals -3. And then, since this is our nice perfect square, we're going to factor it down, and it's always going to be x and then half of this number, so plus 3 squared. And then 27 minus 7 is 20. And we're done. That is vertex form. Okay, so the steps for completing the square, basically what you have to do is if there is one, if there is one, you need to factor out the leading coefficient. So the coefficient on the x squared term, but only from the first two terms. Okay, then you look for your special. Okay, that special number, which is the middle term. I've been doing that in red before, which is the most recent middle term, because your middle term would have changed once you factored out the coefficient from it. So the most recent middle term divided by 2 and then squared. Okay, once you know what your special is, you add and subtract the special number, whatever that special number is. And then you have to remove the negative special number. So the one that you subtracted, you have to remove that negative special from the bracketed section that's going to form your perfect square. Okay, then once you do that, you're going to factor the perfect square. And it's always going to, in the last slide I did it in green, it's always going to be that thing that looks like this, okay? You have x and then something, plus or minus some number. Okay? So once you factor the perfect square, then you're also going to simplify whatever you had left on the outside. Simplify any loose numbers outside the brackets. And then you're done. I guess I probably should add that at this stage, when you remove the negative special from the bracket, you might have to multiply it by the coefficient that's on the bracket, if there is one. Okay, so you can take those down into your notes and then have them forever and study them. Okay, so the reason that vertex form is so valuable that we'll go to all this effort to complete the square is because sketching parabolas is the easiest when you have vertex form. Okay, so the step pattern in a normal parabola. So when I say a normal parabola, I'm talking about y equals x squared. Its step pattern is over 1, up 1, over 1, up 3, over 1, up 5, 7, 9, etc., all those even numbers. So in all of these stages between, you're going over by 1. Okay, over 1, over 1, over 1, over 1. Okay? Okay, then what you have to do in order to make that happen is to plot the vertex before you can use the step pattern. Okay? Now, the step pattern will have changed if you have an a value at the front of your equation that isn't 1. Then you'll have to take your step pattern and multiply it by whatever that a is. So in our example, we, of course, have an a value so that I can show you what this looks like. So normally, our step pattern in y equals x squared would be 1, 3, 5, 7, 9, 11, etc., etc. But because of this -3, we have to take our step pattern and multiply by the -3. And basically what that does for us is it's going to make our steps all bigger, which effectively is going to make our parabola look stretched out. And if you remember from grade 10, we did call this a vertical stretch. Okay, so our new parabola, its step pattern is going to be -3, -9, -15, -21, and I can't imagine we'll get any more on this graph, so I'll stop there. Okay, so first I'll start by drawing y equals x squared, which is the most basic parabola. For y equals x squared, it starts at 0, 0, because 0 squared is 0. If x is 1, y is 1. If x is 2, then y is 2 squared, which is 4. If x is 3, then y is 3 squared, which is 9. So 4, 5, 6, 7, 8, 9. So I just want to point out for a sec, so you'll notice this is that step pattern I was talking about. Over 1, up 1, over 1, up 3, over 1, up 5. Next would be 7. Okay? Then you can do the same thing on the other side to make it symmetrical, and then connect the dots. So that's what y equals x squared looks like. That's just y equals x squared. But we're really more interested right now in this other equation, this -3 times x plus 3 squared plus 10. So we start, step 1, by plotting the vertex, which is hk. So h is 3 here, but notice that like in the general form, there's a negative right here. So that means that our h is actually -3 and our k is 10. So in our case, the vertex is -3, 10. You just have to change the sign of the x. So -3, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is right here. So now from this point, we're going to follow our step pattern. That means that we're going to go over 1, down 3, because our step is negative, and then over 1 from there, down 9, etc., etc., etc. So from here, over 1, down 1, 2, 3. Over 1, down 1, 2, 3. Over 1, down 9, 3, 6, 9. And then same on the other side. And then from there, down 15. 3, 6, 9, 12, 15. And same on the other side. Okay, now we have our points that we can connect in a curvish sort of fashion, which is really hard to do on this board. Sorry. Okay, creating that really skinny parabola. So you'll notice that the blue parabola compared to the red parabola is skinnier, and it's also opening the other way. So its concavity is down, whereas the red parabola has a concavity, it is concave up. Okay, so that's what effect that -3 has on the front. It causes a stretch and a flip. So flip because it's negative, a stretch because it's a number larger than 1. Hope that helps. Okay, so that's what the whole thing was all about, was converting standard form into vertex form. And then I also added at the end how to graph them. I review that in another video, but just thought that I'd add it in since it's related to this idea of completing the square for the purposes of finding the vertex form.